When you configure a router interface IP address, you might think you're done, but the router's not. In this video, we'll talk about the behind-the-scenes activities the router does in reaction to that address being configured, and see how to use show commands to verify all those activities. Let's get into it. For context, this content matches content you'd find in the official Cert Guides, Volume 1, Part 5, Chapter 17 in the current edition. And in that chapter, you'd find three major sections. The second of those is configuring IPv4 addresses and connected routes. And that connected routes part is where we'll focus to begin this video. I'll talk about what those connected routes are, some related routes called local routes that are far less important. And once we're through that, we'll talk about ARP tables and how to look at the ARP tables you'll see on routers. And those are the two core topics for this video. And then there's one completely tangential topic about some common mistakes that can be made with the IP address command. As usual, if you'll stick around to the end, I'll give you some advice about how to study this after you're done with the video, particularly review activities here at the channel, as well as what to do with that content in the book. All right, you know the drill. Let's get into it. Let's start by talking about connected routes. And to do that, I need a scenario. So we'll use this network topology with four routers, R10 on the left where we'll focus, and three branch office routers, R1, R2, and R3. All the LAN switches are layer 2 switches, so they're not doing any routing. All right. So at some point, someone will plan an IP address scheme. That was all in part 4. I'm not going over it again, but here are the addresses chosen for the various routers and the router interfaces in that design. But where I want to pick up the story is that now you can do the math at this point in the course where you figure out what are the subnet IDs you could calculate from this address and mask pair for each interface. And there are the subnet IDs, and I've shown you that. Now, of course, I've chosen a /24 mask, which makes the math a little bit easier. And those are the subnet IDs. And the reason I mention that is this. If I focus here on router R10 and its 5 interfaces, it's connected to 5 links, 5 places where we would expect subnets to exist. And it's going to have 5 connected subnets and 5 connected routes when everything's up and working. So what do I mean by that? Like up here on this gig 01 interface, we'll configure an IP address on that interface, and the router is going to create then a route for that subnet and mask and add it to the routing table. And when we configure interface gig 02 with an IP address and mask, the router will create a route, a connected route for that subnet ID and mask. And likewise for those 3 WAN interfaces, when we configure IP addresses on those, the router will create connected routes for those 3 subnets and add those to the routing table. So let's explore that for a few minutes. So what makes all this happen? Well, it starts with these IP address configuration steps. So here we are on router R10 again with those 5 interfaces. The 5 interfaces are shown here with the interface gigabit whatever commands with ports 01, 02, 010, 020, and 030 with their respective IP address commands that match that big table. All right, so there's the configuration. In reaction to that, then, if you use the show IP route command on that router, you're going to see some routes. And the ones with a C in the far left-hand side are the connected routes. So let me talk you through the output for a moment. First off, show IP route begins with a legend of codes, and it's about 10 lines, and the first 2 happen to be L for local and C for connected. Those are the ones I'm going to talk to you about here in the next few minutes. C for connected just says that's a connected route. Now, if you look down here, we've got a heading line that says, hey, we're subnetting Class A network 10. That's this 10.0.0.0 with the default mask of /8 designated there. And the router knows about 10 such subnets with 2 different masks, and then indented are the individual routes. And if we glance, we see 3 connected routes with these 3 dots signifying we're out of space on the PowerPoint slide. Now, I want to show you all the connected routes, and I couldn't show them to you with this big legend taking up all the space. So in the next slide, all I've done is I've removed the legend, which left space for all 10 of the routes, and a bigger font to make it easier to read. All right. So now if you glance down through here, we've got all these connected routes, and we've got these other routes with an L that are local routes. I'm ignoring the local routes for now, all right? I just want to talk to you about connected routes for a moment. In fact, I want to just totally focus on the connected routes so badly, and I'm going to show you the next command in the next slide. On a real router, you can use the command show IP route connected, and it really will show you only connected routes. It will show the legend, which I've omitted in the slide just so I can use a bigger font. And it will give you the same heading line. It will mention all the known subnets by count, but it will only list the connected routes. So here are our 5 connected routes. So if you think back to that diagram that showed the 5 subnet IDs connected to router R10, here they are: 10.110, 10.220, 10.2.101, 10.2.102, and 10.2.103. And it shows them all as directly connected routes. That is, there's no next hop router. And it shows their respective outgoing interfaces of 0.1 gigabit, 0.1, 0.2, 0.10, 0.20, and 0.30. So to finish up talking about those connected routes, what are they for? Well, they're there for routing to those connected subnets. For instance, router R10 on this top interface, once it's got a connected route for that subnet, it can forward packets to destinations in that subnet. And likewise for the lower subnet, and likewise for those 3 WAN subnets. Additionally, when you turn on a routing protocol, which we haven't talked about in class yet, but once you do, that's how adjacent routers can tell each other about known routes. Well, now router R10 knows about some routes that it can tell its neighbors. Those neighboring routers now would have routes to these 5 subnets as well, and so on and so forth, so all routers could have routes to all subnets. Additionally, let's think about what's happening with this dynamic process to add connected routes. Routers will also remove them. The router removes connected routes if an interface fails or if you unconfigure an IP address, like with the no IP address interface subcommand. For instance, if you do a show IP interface brief command, you'll see the line status and protocol status of each interface. Now, all 5 of these interfaces are up and up, and they all have IP addresses configured. So here's the deal. If an interface has an IP address configured and it's in an up and up state, the router adds a connected route for that interface. But if the interface fails or you remove the IP address or both, then the router removes the connected route from the routing table, all right? But if it's there, any routing protocols are going to want to advertise about those connected routes. And again, the goal, the purpose of these connected routes is to provide routes to those connected subnets. Now let's wrap up that topic I'm trying to avoid. It's called local routes, and these exist. They've existed for decades on Cisco routers. Honestly, I wish they didn't. So when you configure an IP address on a router interface and the interface is in an up state, Cisco also adds a local route. And the local routes have a /32 mask no matter what mask you configured. So a route with a /32 mask means this is a route for exactly one IP address. And the IP address shown is the IP address you configured in the IP address command. Notice all those IP addresses we configured earlier ended in .254. And so all these local route IP addresses end in 254 in this example. All right. So what are they for? They're for internal processing in the router based on a feature Cisco added some couple of decades ago. And they're there, you see them, they clutter up the routing table, but there's nothing you go out to take advantage of with these. You just have to be tolerant to the fact that it clutters up the routing table. All right, so you see them. If you configure the IP addresses on an interface and those interfaces are up, you'll see local routes. And just like with connected routes, if the interface fails or you remove the IP address, the router will dynamically remove the local route from the routing table, all right? So you'll see the pair, the connected route and the local route, appear and disappear with that same set of rules. One thing that is different, though, is that routing protocols, they don't advertise these local routes to other routers. Again, they're just there for some internal processing on the local router. So you can see them, you can say, Wendell says I can ignore them, and ignore them. Today's video is sponsored by me. That's right. So if you want to give something back to the channel to help it grow, click subscribe, click like on every video, or use this QR code or link when you do want to buy something. You don't pay anything more, and I'll make a few dollars back from those booksellers. All right, let's get back into it. This is also a good time to revisit ARP and then drill down on how to look at the ARP tables on the routers. All right, so let's do that. Here we're on router R10 again, and in this case, R10 has the required entries in the ARP table, but hasn't learned any ARP table entries for other devices. So if you take a look at this command, show IP ARP with no other parameters, we have 5 IP addresses listed. And it says the minimum age is a dash, and you're going to see these entries anytime the interface is configured with an IP address and the interface is up. Sound familiar? And what the router will do is add an ARP table entry for the interface IP address, its own address. All of these are addresses configured on the router interfaces. And instead of a number, which shows the age, how long it's been since the entry has been used, it shows a dash to signify this is one of my own IP addresses. These entries will stick around forever. Now notice over here in the interface column, it lists the different interface IDs for the 5 interfaces from which these addresses were taken. Now for entries that are learned dynamically for endpoints that are connected to those subnets, you'll see output like this. For instance, consider interface gig01 off router R10. You can do the show IP ARP command, and if you want to, you could even list the interface ID. And that only lists ARP entries for that interface. In this case, that interface is connected to subnet 10.110/24, so we'd expect to only see IP addresses in that subnet here. In this case, we've got the router's own IP address. We know that because of the dash here in the age column. It tells us, hey, that one doesn't time out. Whereas 10.111 would be some device in that subnet. And 12 minutes ago, the ARP process completed and the router learned that IP address and matching MAC address. Over time, this number will continue to grow until the ARP process repeats. So this ARP entry could be used thousands of times, and this number does not reset, it keeps growing. But before the default 4 hours timeout completes, the router can do things to refresh the entry so it never times out. For another example, consider interface gig02 with the other subnet. You'll see just entries in subnet 10.220. You see no timeout for the router interface IP address and a growing timeout value for the one endpoint device that's been learned and in the ARP table so far. This is also a great opportunity to think about how do these connected routes work with the ARP table, or in sequence as it turns out. So imagine this router R10 and a packet arrives and it's destined for PC12's address of 10.221. So what's the logic here on R10? Well, it's going to match the packet to the routing table and it's going to match that connected route for subnet 10.220/24. But that packet, once it's de-encapsulated, we need to re-encapsulate it in a new data link frame. And the information needed to re-encapsulate it is in the ARP table. So the router is going to match that destination address 10.221 to the ARP table and find the matching ARP table entry, and only then re-encapsulate the packet. So what am I talking about here? Well, let's first look at the connected route. There it is, 10.220/24. It's directly connected off gig02. So then the router knows, hey, I need an ARP table entry that's off of interface gig02. Well, here's show IP ARP gig02 that tells us what are those available entries. And here's the address 10.221. So it's already in the ARP table. Now, brief aside, if it wasn't here, what would the router do? Right, it'd send out an ARP request, expecting to get an ARP reply and fill up the table with an entry for 10.221 and learn its MAC address. But here, we know its MAC address. So now router R10 can encapsulate this packet in a new data link frame, and it looks something like this. A destination MAC with mostly B's in it, taken from the ARP table in effect. And then the destination IP address we already knew was PC12's 10.221. So that's some of the interaction, or the dependence, if you will, of matching the connected route in the routing table, and then for re-encapsulation using the ARP table entry. Next, we have one more topic that, quite honestly, it just doesn't fit very well anywhere else, so had to put it somewhere. Here it is. So here's the deal. There are a few issues with the IP address command in terms of you can type parameters that don't really work, and you get an error message, and the error message can be a little confusing. So here we go. You cannot configure a value that's a subnet ID or subnet broadcast address in the IP address command. But the error message, confusing, I think. So here we are in interface config mode. You type this command, 10110 with this mask is a subnet ID. But the message doesn't say you typed a subnet ID. You can't do that. It says bad mask /24 for address this. Or if you typed this other command in interface mode using a subnet broadcast address, then you get the same message. It doesn't say you typed a broadcast address. All right, so it's not very smart about telling you what your problem is. But if you see bad mask in response to your IP address command, chances are you typed an incorrect subnet ID or an incorrect number that happens to be a subnet broadcast address, particularly when it says bad mask with a /24 style mask, prefix style mask. You can also make this other mistake, which is probably harder to make because it would just look weird to you, if you use an illegal subnet mask. Now, notice it says 255.192.128.240. It's just illegal. Why? Well, the underlying binary value can have all ones on the left and all zeros on the right, but you can't interleave them. And if you converted this to binary, you would see that it's interleaving ones and zeros. So you get another bad mask message. It doesn't say you typed in illegal subnet mask. It says bad mask. All right, so that's maybe a little more accurate. Then it gives you the mask in hexadecimal that you typed. So this is the hex equivalent to the number you typed again. So anytime you get this kind of error message, know that the IP address command was not accepted. You typed something incorrect. Check your parameters and figure out what you did wrong. There's one other design-related issue that'll show itself with an error message on the IP address command. So the design you see up here on the left is legal. So the design is where you've got two different routers connected to the same VLAN and subnet. Perfectly legal, normal to do, popular to do. And these two routers can mutually support each other in their role as the default router. In fact, there's a whole series of protocols called first hop redundancy protocols that they use to support each other to do that. You'll learn about it later in the CCNA course. What's illegal, and not obviously illegal at first glance, is one router, two interfaces connected to the same VLAN and subnet. That's illegal. And the mechanism that's used to prevent that from happening is this. You go into that one router, you can give it one interface with an IP address and mask that attaches to this subnet. But as soon as you type a second IP address command on a second interface that would place it in this same subnet, you get an error message on that second IP address command. And it says 10110 overlaps. So that's the subnet ID in this case. So it overlaps with that first interface. So the IP address command is rejected, the address is not taken, and you still only got one interface connected to that subnet. That's the meaning of that particular error. Welcome to the study group discussion. So what do you do with this stuff moving forward from here? Make a habit. Anytime you're in lab here forward and you've got IP addresses configured in the lab, go check out those routes that the router automatically created. Check out the connected and even the local routes just to make sure you understand what's there. And take the extra time to look at the ARP table entries, especially after you've generated some traffic, if you're practicing in Packet Tracer, and look at those and make sure you see which connected subnet they're in. In fact, right now, I think it's time to go practice extending a config lab. The config lab I'm pointing you to here, config lab 203, called IPv4 addresses 3. The lab itself is focused on just completing an address plan and configuring the addresses, but once you configure the addresses, the interfaces are up, you've got connected and local routes, take a look at those, predict which connected routes you would expect to exist here in this 3-router network, and then check to see that they really are created. So that's the drill there. For the book itself, it's a great case of, hey, this is a show command intensive section interpreting what the show command output is. So there are several different examples and topologies in that section of the book. So check out those examples and make sure you understand those for more practice in figuring out what does the router do for you in response to configuring an IP address. I hope you enjoyed the video. If you're ready for the next instructional video, It's about static network routes. All you have to do is click on the link on the left. If you're ready to practice that config lab, the intro video for that lab is over on the left, and of course the lab itself is available on a blog post linked in the description. Hey, thanks for hanging out. I'll see you in that next video.